Okay, so let's start. Okay, let's start. Section 0.5, Factoring Polynomials. So during this section, we're going to recall how to factor polynomials. First off, this is very similar to how we factored integers. So if you have some sort of integer, then you would like to factor it into two integers, neither of which is one, hopefully. And if you're able to do that, then each of those are called factors. If you're not able to write it as the product of two integers, neither of which is one, then we say that the integer is prime. With polynomials, it's very similar, and the techniques are somewhat similar to factoring polynomials as it is for factoring integers. So if you have a polynomial and you're able to find two polynomials, neither of which is primitive, then we say that you can factor your polynomial. Otherwise, we say that the polynomial is irreducible or prime. So the first technique that we will cover when factoring polynomials is, well, factoring out the greatest common factor, the GCF. On page 61, let me do problem number 14. In each expression, factor out the greatest common monomial. So let's do that. So first off, if I look at the integers, just try to find the greatest common factor of those integers. So 25 and 15, well, the greatest common factor is 5. For the polynomial part, it's actually easier than even the integer part. You'll just look for the lowest power in common, y squared and y, so y, z and z squared, so z. Let's divide 25y squared z by 5yz, and so I get 5y. Negative 15yz squared divided by 5yz is a negative 3z. There is nothing I can factor out from this term in the parentheses, and so I am done. The next technique that we'll be looking at will be factoring by grouping. So in general, when you're factoring, the first thing you should look at is see if you can factor some sort of greatest common factor out, and then use one of the other techniques. Factoring by grouping is more of an art than a technique. It's very powerful, but sometimes, well, especially I guess I'll give you an example at the end. It can be sort of tricky to understand how you should group. And so I will first give you examples where it's trivial. So let me do problem number 18, factoring by grouping. So in each expression, factor by grouping. So the first technique is to just group the first two terms and the last two terms. If this works, then you're very happy and you can factor it. Otherwise, you may have to do something else and eventually be able to factor it by grouping. Okay, so let's first see, well, there's an x here in common in the first term. And what remains is just x plus 4. In the second grouping, there's a y in common. Factor out the y. And so, what's in common in these two terms is x plus 4. What remains after I factored out the x plus 4 is just x plus y. And so that is my answer. Okay. So let's recall special factoring. Okay, so the difference of squares, maybe I should write that down. Or the product of the sum and difference of two terms is, well, again, you memorize this when we gave it as the special product formulas. Now we're going to write these as special factoring formulas. And so a squared minus b squared is just a minus b times a plus b. Next, note that the sum of squares is irreducible over the reals. You can factor it over the complex numbers, but as far as factoring over the reals, you can't do that. Okay. And so this is the sum of squares. Next, I have the perfect square trinomial. And I'll just write it as one formula rather than as two formulas by just utilizing the plus or minus. So a squared plus or minus 2ab plus b squared is just equal to a plus or minus b quantity squared. Okay, so let me move this up one. I have the sum of cubes formula. A cubed plus b cubed is a plus b times the quantity a squared minus ab plus b squared. I have the difference of cubes formula. Notice that the sum of cubes and the difference of cubes formula are very similar. I'll point out the differences between the two, how you can memorize these. So a cubed minus b cubed is a minus b quantity times a squared plus ab plus b squared. So notice that this sign here is the same as this first sign. The second sign is always opposite the first sign. And everything else is the same. So this should not be difficult to try to memorize them. So let's use the special factoring formulas. So in each expression, factor the difference of two squares. So if it turns out that your polynomial is of a particularly simple type, so you can use these formulas, then you should use them. So I have here 81 minus x squared. So you notice that this is the difference of squares. 81 is a perfect square, and so is x to the fourth. So this is the same as, well, oops, 9 squared minus x squared squared. So this is just equal to 9 minus x squared times 9 plus x squared. I can factor this. 9 minus x squared can be written as 3 minus x times 3 plus x. That's the difference of squares. However, 9 plus x squared is irreducible prime over the reals. So I've completely factored this over the reals. There are no other polynomials, factors of any of these terms where the coefficients of that polynomial are real numbers, other than if you multiply by 1, other than if you multiply by some primitive polynomial, a unit. Okay. Let me do problem number 32. In each expression, factor the trinomial. Okay, so this is just equal to, well, the square root of r squared is r. The square root of 16 is 4. The square root of s squared is s. So let's check if the middle term works. So r times negative 4s is a negative 4rs times 2 is a negative 8rs. So you get the middle term. Therefore, using the perfect square trinomial formula, this factors. Let me do problem number 34. Well, there's really nothing you can do with this guy. So I have 8x squared. I'll write that as 4x times 2x. I have here a negative 3y squared. So I'll factor that into negative 3y times positive 1y. Now let's check to see if I've factored this correctly. So 4x times 2x is 8x squared. Good. 4x times negative 3y is a negative 12xy plus 2xy gives you a negative 10xy. Y times negative 3y is a negative 3y squared. And so I am done. In each expression, factor the difference of squares. Difference of squares. Difference of cubes. Okay, so it must have said difference of cubes, because this is a difference of cubes. Okay, so the cube root of 125 is 5. Cube root of a cubed is a. Cube root of 64 is 4. You keep the same sign. 5a squared is 25a squared. Change the sign from negative to positive. 5a times 4 is 20a. 4 squared is 16. And so you're done. And you factored this completely over the rationals. Actually, let me show you that this is factored completely. So let's just recall. The discriminant. So if I look at my discriminant, 4, so 5a minus 4, well, obviously that's factored as much as possible. It's a linear factor. Let's look at this quadratic, and let's see, can we factor this quadratic? So b is equal to, well, 20. A is equal to 25. And C is equal to 16. And so D is 400 minus 4 times 25 is 100 times 16 is 1600. So D is equal to a negative 1200, which is less than 0. Recall that if your discriminant is less than 0, then that says that you have two unequal complex roots. Or well, I should really say complex, so not only they're actually non-real roots. Which says that, as a consequence of that, that says that this last term cannot be factored over the reals. And in particular, since this is not a perfect square, D is not a perfect square, then I know that you can't factor it over the rationals either. So neither the rationals nor the reals can you factor this. Okay, so yes, indeed, this was a correct answer. Let me do problem number 101. Factor each expression completely, meaning over the rational numbers. If an expression is prime, so indicate, meaning if it is irreducible. So let's try to factor this. Notice that this is quadratic in x cubed. So I can factor this as x cubed, x cubed. Now this is a monic quadratic trinomial in x cubed. So let's bring down the plus times minus is minus. I want two whole numbers whose product is 8 and whose difference is 7. So 8 and 1. So now, using the sum of cubes formula, I get x plus 2 times x squared minus 2x plus 4. I can factor x cubed minus 1. It's the difference of cubes. So x minus 1 times x squared plus x plus 1. And I claim that this is factored completely over the rationals. So again, let's look at my discriminant. And so my discriminant is just b squared minus 4ac. And so let's look at x squared minus 2x plus 4. So in this case, b is negative 2. A is 1, and C is 4. So this is 4 minus 16, negative 12. Again, this is less than 0. So just like above, this has two unequal complex roots. complex non-real roots. So that means that this cannot be factored over the reals. Next, let's look at x squared plus x plus 1. So my discriminant is b squared minus 4ac, 1 minus 4, negative 3. This is also less than 0. So same, we have unequal complex roots. So it doesn't factor over the reals. Okay. So this is completely factored. Over the reals. Okay, so let's look at the following example. X to the fourth plus 2x squared plus 4. Let's try to factor this over the reals. So let's try to do this. Okay, so let's factor this by grouping. And let's do the following. Let's add 2x squared, subtract 2x squared from the second term. Notice that now this first term is a perfect square, and so is the second term. I'm factoring this over the reals. So this is equal to, well, I can factor this because it is the difference of squares. So I'll factor this as the product of the difference and sum of two terms. So this is equal to, let's write it in nice descending order as x squared minus rad 2x plus 2, x squared plus rad 2x plus 2. And that is completely factored over the reals. Again, you could check that this was completely factored by doing the same sort of deal that I did above by looking at your discriminant for each of these two. So this really finishes off section 0.5. So that's it for today.